Okay, problem number 4. 8 points for getting the complementary solution. Okay. 5 points for the Wronskian. Okay. Now we got to get U1 and U2. And again, just like when I wrote down the method variation parameters over here, I said integral secant is log secant plus tangent. And again, that's not just to throw you off. If you didn't have to use that, it's kind of a hint at, oh, you must have made a mistake someplace, right? Not going to give you superfluous information. Okay. So we got to get U1, U2 now. Okay. And I have the formula there for U1 and U2. U1 prime is minus Y2F over the Wronskian. So, just plugging into there, we have the derivative of U1 with respect to X is minus e to the X cosine X, right? Minus Y2, which is that. Right-hand side, e to the X tangent X, divided by the Wronskian, which is minus e to the 2X. I remember I had said in class many times that I'm not going to give you anything really difficult to integrate. If there is something that's difficult to integrate, I'll give it to you. So other than having the integral of, which one is it here they give you? The integral of secant, everything should be pretty straightforward. Okay. So what happens, of course, is that the exponentials cancel. Tangent times cosine, right? That becomes just sine of x. So U1 is minus the cosine of x. Let me see, for U1, how much credit did I give? 5 points for U1. Okay, it's really just plugging it in and doing an integral, right? Okay. U2 is a little more difficult, so I didn't want to make it like 6 and 6. I made it 5 and 7. So I gave 7 for U2. What about U2 now? Okay, the derivative of U2 with respect to x, just doing variation of parameters, is first solution, which is e to the x sine x, times the right-hand side, which is e to the x tangent x, divided by the Wronskian, minus e to the 2x. And this will give you minus sine squared x divided by cosine x. And I think there was one in class that I just like this. Okay, so you should remember what to do. Okay, so the derivative of U2 with respect to x, use the identity sine squared plus cos squared equals 1. That becomes cosine squared x minus 1 upstairs divided by the cosine of x. And then that gives you the cosine of x, and there's that secant coming in. Okay. So now we integrate this. We find that U2, integral of cosine is easy. That's the sine of x. And then we just grab the result for the integral of secant, log secant plus tangent. Okay? And then you have to do the particular solution. Okay? Y sub p is equal to U1 times Y1, which in my case was e to the x sine x, plus U2, which is this mess over here, times my second solution, which is e to the x cosine x. Okay? And if you plug in for U1 and U2, I didn't take off credit for this, you'll find out a certain term cancels. I think an e to the x sine cosine cancels. Okay? And therefore, you'll find that the general solution is the homogeneous, which is, we got that right over there. Let's just do this, e to the x parentheses c1 sine of x plus c2 cosine x. Okay? And again, if you just wrote yc plus yp, that was fine. Okay? And then the particular solution, actually when you do this and you simplify, you'll find it's just minus e to the x cosine of x times the logarithm of secant x plus tangent x. Okay? So it's minus e to the x cosine x log secant plus tangent. Okay, again, go over the points for that again. 8 points for getting the complementary, 5 for the Wronskian, 5 for U1, and 70 points for U2. Okay.
Professor, you skipped number 3.
Oh, I do
Cauchy Euler.
Okay, let's do number 3. Yeah, that's a Cauchy Euler. Okay. Yeah, this is good. I'm glad you told me those, because this is where a lot of people screwed up. And it's not really that much to, I think hard to remember, because you remember when you have constant coefficients, you plug in EDRX, that's how you keep getting like R squared EDRX or cubed EDRX, EDRX cancels out. Clearly that's not going to work on something like problem number 3. If you solution form EDRX, okay, you're going to get, you have to be able to solve for R and get a constant out of it. And that's another thing, both in the method of term coefficients, both in the case of a Cauchy Euler, right? You assume a solution x to the R is a constant, right? So R can't be a function of x. And when you do the common case of constant coefficients, you assume a solution of the form EDRX, R is a constant again. What a lot of people did is they'll just write, they did things like on number 3, they did x cubed R cubed plus 2x squared R squared minus x. You're just kind of doing things from rote, okay? It doesn't make any sense, because what happens at the end, your R is a function of x, right? And it's not even a solution. It violates, what you started with, right? So please keep that in mind, okay? For most cases, when it's constant coefficients, the trial solution is e to the Rx, okay? And you know all the cases of a double root and complex root. And it's only the Cauchy Euler where we assume x to a power, okay? Okay, so let's do this one. You got it in front of you. It's a homogeneous equation. It's linear but has variable coefficients, right? So I've got to get the, so since it's a Cauchy Euler, we assume a solution of the form y equals x to the r. Y prime is going to be r times x to the r minus 1. And y double prime is r minus 1, x to the r minus 2. So what's L operating on y? First term of the equation looks like x cubed times the, do one more derivative, sorry. Y third derivative is r minus 1, r minus 2, x to the r minus 3. Okay. So the first term of the differential equation is going to be x cubed third derivative. So it'll just give me this, x to the r, but we know x to the r is going to knock out at the end. So it's just r minus 1, r minus 2. Okay? Then we have, next term is plus 2x squared second derivative. Plus 2, if I do x squared times second, that just gives me an r minus 1. Okay? And the last term is plus 2 times y. Plus 2, x to the r, which goes out, is equal to 0. Okay, that's the cube. Let's see how I did this. R minus 1, r minus 2 plus 2, r minus 1 minus r plus 1 0. Okay. What I did is, let me just look at this. R plus 2, r minus 1. Something's wrong here. Let's go back. Plus 2, x squared second derivative is r minus 2. Right? I need 2 x squared second derivative, right? No, that's right. 2 r minus 1 plus 2 is equal to 0. Different over here.
It should, what I have is,
Look at my notes. Let me just, r minus 2 plus 2 r's. I got the minus r plus 1.
yeah, I have a plus 1 as well.
So, yeah. Oh, yeah, I keep looking at the wrong problem. Sorry. Yeah, so I'm going back and forth on these pages. So I get the 2x squared second derivative gives me that, right? Then minus x dy dx. So minus x dy dx is a minus r, right? And then finally plus y plus 1 is equal to 0. Okay. And the idea now is I can factor out r minus 1 from everything here. R minus 1, right? Let's see. R minus 2, right? Plus 2r, r minus 1. And clearly this is just minus 1 times r minus 1, right? Negative r plus 1. So I was hoping that people were able to factor it, not like have to expand and get a cubic, and then that's why at the end I told people r equals 1 is a root. Okay? But you see, we do it this way. If you just see r minus 1 every place, you don't even have to cube it, or get it to a cubic. Okay. So let's just do a little algebra over here. We're gonna have r minus 1. We're gonna have r squared, right? Minus 2r plus 2r goes out, right? Minus 1 is equal to 0. So that becomes r minus 1 squared, r plus 1 is equal to 0. Right? And remember, I always emphasize this, basically the characteristic equation is a cubic. The differential equation is third order. You need 3 independent solutions. Okay? So we have a root of negative 1 and a double root of 1. So, corresponding to r equal to 1, we're going to get c1x, right? And now we have a double root of 1, so it's going to be x log x for the second guy. C2 x log x. Remember, we covered all these in class. What happens when you get multiple root, complex root, etc. And even if you forgot about the x log x, what you can do in your mind, this is what I always do, is remember that what we showed for this Euler-Cauchy equation was that if you made a substitution x equals e to the t, it converted to constant coefficients. Okay, so x equals e to the t, constant coefficients. What would happen if I had a double root of 1 and I did it, with a constant coefficient? I'd have e to the t and t e to the t. Well, e to the t is the x, and there's t e to the t because t is log x. Okay, so. Okay, and then finally, plus another arbitrary constant times x to the minus 1 power. Now, that's probably the easiest one in the sense of, as far as amount of work you have to do of all of them. Okay, and how did I do the credit on problem number 3? Let's see. Okay. $10 for the characteristic equation. Yeah, if you got to here, those 10 points, a little bit of algebra, let's see over here, 10 points, right? You got the characteristic equation, 10 points. And then 5 for the roots, okay? 5 for roots. Because I realized as I was grading it, that some people got the characteristic equation, wanted people to get the roots. I didn't want to take off full credit, so I made it, okay, let's get most people most credit. Give them 10 for the gain characteristic and then just 5 for the roots. Because if you got both, then great. And then, I guess it's 10 for the solution. Okay? Realizing, of course, with the x log x. Okay? Okay, so I guess that does it. And like I said, the average was, I had it here someplace, 76. Yeah, 76. Okay. Okay, we still have half an hour, so I'd like to go on. Okay, everybody got the test back? Good, okay. Next problem that I want to do, again, some of these, like I said, I like to do applications towards the end. This one actually comes from the book, and I think it's a really interesting problem. Okay? I should put the diagram on the board first. Here, this one. one of the, I forgot, I think it's the end of chapter 4 of linear models or something. There's quite a few interesting problems that they have. This is one I thought we could go over and have some nice graphs to show you. Okay? Basically, it's the following, okay? We got a coordinate system over here, and this is a guy who's like swimming, okay, from, I guess, one shore to the next, okay? So let's say this is the one shore over here, the east. This is the west. Okay? And he starts off at the point 1, 0. Okay? And what he wants to do is he wants to land up at the origin. So there's a certain point he desires that he wants to swim to, starting at 1, 0 over here. Okay? Now, of course, if there was no current, the most direct path, you just swim parallel to the x-axis, right? But unfortunately, there's a current over here that's going like this. Okay, with the speed VR. I guess velocity of the river maybe VR. Okay? So as soon as he starts going in this direction, what's going to happen? The current is going to push him this way. So his path actually would be something like this. And hopefully he'll reach the origin. Okay? And the idea is that when he's swimming, he's basically always directing his velocity towards his goal, right? Swimming, you're basically looking at a point, that's where I'm going to go, so you head in that direction. But remember now, you have to be careful, that would be, he's in the water when he makes that judgment, so that would be his velocity relative to the river, okay? So that's why you have to parameterize it in a certain way, okay?
Is this going for also what is the least effort?
No, it's just that basically we're going to be given VR and VS, and we're going to show that a certain relationship has to hold, otherwise we'll never reach the other shore.
Okay.
Okay? In one case, you'll find out that he hits the other shore, but he's too far north. In another case, the current just takes him away. He starts going like this, and the current just, and have some nice graphs to show that. Okay? So let's just put a little point over here, an arbitrary, this is like making the guy into a little point, okay? The coordinates over there are going to be x of t, y of t, right? Relative to this fixed frame. And then I'm going to go make a little line that goes